had the last ones we looked at a p-series, right? We've also done what? The integral test. That was 2 days ago. Okay. Gee, I thought you'd remember. That was a hint. Gee, I thought. Thank you. Okay. Welcome to school on a Friday. Okay. There's another one. 10.1. Yeah. Term test, right? There is some American algebraic methods. So those are the four. Today we're going to add two more: comparison, limit, comparison. They're very similar. Both obviously drive on comparing two different series in order to determine convergence. Right? So we have 4, 5, 6 today. Next week we add our final 3, and we'll end up with 9. Okay, we'll write cards for all of them and stuff. So comparison test. Assume, and you know what that does? Makes things very nice in mathematics. This is a very, very common way to start a theorem. Okay. Assume that there exists some letter m greater than 0 such that 0 is less than or equal to a sub n, which is less than or equal to b sub n. Those are sequences for n greater than or equal to. If series B sub n converges, then what do you think happens to A sub n? That's because B sub n is on top of it, right? And A sub n's under it. So B sub n stops, A sub n has to stop too, right? It has to converge. So, right. What's the other statement we're going to make then? If what's your statement? Okay. That's it, right there. If A sub n diverges, something bigger than it also has to diverge, right? Okay, good call. You guys were thinking that one through. If A sub n diverges, then, okay, slow down. B sub n also diverges. Okay, so basically what you're going to be given is a series, and you're going to pick another series to compare it to. Okay, so you have to have some level of analysis here in order to pick the appropriate series to compare it to. It's usually fairly obvious, right? Let's look at one like this. Let's say series from n equals 1 to infinity, 1 over square root of n, 3 to the n. Okay, does it converge or diverge? Okay, so what I would advise you to do is say, okay, there's no nth term test. Okay, we go through all of our easy ones, right? P-series, this is not a geometric series. This doesn't meet any of those criteria. But is there a geometric series or a P-series or something that we can use that's bigger than this, that converges? So, is there something that this is less than or equal to, and it's just a play on the denominator, right? So, is that true? Okay, is this denominator bigger than this one? It is, right? So that means the fraction is actually smaller, correct? Right, so we are making a smaller denominator here, but a bigger number right here. So that's one of the ways we can manipulate this. What kind of series is this? Geometric. And what is the R value? It's 1/3, right? Okay, so geometric series R is 1/3. Does it converge or diverge? R is less than 1. It converges. Yes. Right? There you go. That's the comparison test. Right? So since you make your statement, since series from n equals 1 to infinity let me restate that. We want to make that statement too. Right, they all have to be positive or 0. And since this is true and the series is larger converges, we know that this happens. Easy enough. Again, I got the hard parts picking the comparison. It's a really high level of thinking, but try to keep it simple. Use the P series and use the geometric series as much as you can. All right, so use geometric P series if possible. evaluate that beast. It's very ugly, yes, thank you. But we can compare it to something very not ugly. Do you have any ideas on either end? Is that geometric or p-series? Okay, 1 over n squared. That's p-series, right? Which side would it go on? Greater than or less than? Think about the 1/3 here. So 1 over n squared is smaller? I think you're right. Converge or diverge? Right. This converges, right? Okay, does that tell us anything about this one? It does not. Right, so this has to be bigger in order for this comparison to work, correct? All right, so we can't use that comparison, right? So sometimes you've got to kind of guess and check. Okay, think about this. Those are very similar, correct? Because of the exponents. Is there something that's very close to this that diverges? Something smaller that diverges? Or is there something larger than this that converges? We can't really say that these two can be compared because there's so little difference here. We want something that's pretty, let's try this. This has a bigger denominator, so it's a smaller number, correct? All right, does that converge or diverge? It's a p-series, right? This diverges. Yeah, it's a p-series. P equal to 1. Now you could make your statement, right? That's you. So again, pick those wisely. P-series, geometric series are pretty much going to be your go-tos. And it's going to be, see how that has an exponent number? Probably a p-series. The one before it had an exponent n, probably a geometric series, right? So, do you want me to write this statement out? Okay, since 0 less than or equal to there is another example of picking your other sequence carefully, if you want to look at it. I already went through it. All right, limit comparison test. Guess what? This uses limits. It's a little bit more wordy. Let A sub n and B sub n be positive sequences. Again, conditions, right? Have we looked at any negative series of sequences? We could do negative geometric series, but most of our tests are positive so far, right? Okay. Ooh, that sounds fantastic. So we have some limit. That's the ratio of the two sequences, right? If L is greater than 0, then that's not what I wanted, right? All right. So L is greater than 0. Series of A sub n converges if and only if B sub n does what? Converges or diverges? So what this is saying, if you compare the two in a limit, and L is equal to 1 or 10, a number bigger than 0, right? If either one of them converge, the other one does as well. If and only if, have you heard this before? Okay, that's a statement that goes both ways. Like, if A sub n converges, then B sub n converges. Also, if B sub n converges, then A sub n goes both directions. But if L is bigger than 0, this limit, then they both have to converge. As long as one of them does. If one of them diverges, and this is true, they both have to diverge. So they are very limited. Okay, what happens if L is infinity? And A sub n converges? Then, boy, I am habit prone on that one to write n equals 1 to infinity. You guessed it. So basically, this is very similar to the comparison test, right? A sub n has to be larger because this is an infinite limit, correct? So if A sub n is bigger and it converges, B sub n has to converge. Right? So that's the big thing there. It's I would bet money this proof is based on the comparison test, to be honest with you. Okay, one more. If L equals 0, B sub n converges, what happens to the A sub n? It did? Well, it's supposed to be converges. Alright. So if L equals 0 and B sub n converges, that means the bottom is bigger, right? The bottom is bigger and it converges, what has to happen to the top? A sub n. That's converge as well. Right. This is a comparison test again, just in a different format. I would say you could do the contrapositive. Remember that? So for C, if L is 0, if A sub n does not converge, B sub n does not converge. Right? Because B sub n is larger than A sub n. You can use the contrapositive on this too as well. If L is infinity, B sub n does not converge, A sub n does not converge. Right? You can use that logic to make that connection. So let's look at one. Alright, let's a lot of times you'll have a tagline that says show that it converges. You actually know the answer, you just find it. Right. Notice how there's something on top. This is where you're going to want to probably default to the limit comparison test. The comparison test, notice we had ones on top, right? So there's a key indicator of the difference between the two. Alright, so this one is prime for the limit comparison test. We're going to let A sub n be the series. We're not picking A sub n and B sub n top and bottom here, okay, because they both go to infinity. And that's what I just cautioned you at. We want to prove that this entire fraction converges, so we have to compare that whole thing to something else, right? We're going to choose that something else to be a P series equal to, right? Because if you take the limit here, it's 1 over n squared, right? That's how you would attack this problem, right? So that's how we're going to tackle this. We have basically chosen this based on what we have here. So, what is the limit? As n approaches infinity of Fraction division means we do what?
Students that are going to the solo ensemble today.
Oh, bummer. I'm sorry, you have to miss the rest of this. But you can figure this infinite limit out, right?
Yeah.
We have n to the fourth over n to the fourth, which is so because we just use the highest exponents, right? Okay, which is 1. Right? Then we're going to look at the comparison test where L is 1. Right? Okay, 1 converges, they both converge. Does this series converge? P series equal to 2 converges, right? So there you go. Have fun. Perform well.
Thank you. Wait, I have my sister's money. Let me give it to you.
Remember? Oh, very cool.
Yes. I want to see it.
Okay, so since L equals 1 and the series of B sub n converges, right, that's P series, P equal to 2. Series A sub n, which we have defined here, also converges. So, a couple things to note here. We would want to do this if we're going to say L equals 1, right? Just to be clear. B sub n we have declared as this sequence, so we can write this out. This is good notation. If I hadn't have put B sub n here, I would not want to declare it this way. I would want to write little raised to it, right? So just be careful in your statements sometimes the way you write it. All right, let's look at one more, and we'll be done. Determine if series converges. So which test do you want to use? The comparison test? That's what you were saying, the geometric one? Possibly. What would you compare this to? Or smaller, greater than converges, or smaller than diverges. No, this is determine if it converges. It doesn't give you the answer this time. That's what we're trying to figure out. Is there, okay, so is there a sequence bigger than this that convergence. That is actually smaller. Because this is basically like 1 over n, right? Close to it. Could we use 1 over n? Okay, 1 over n diverges. So is that smaller than this fraction? Yeah, because this is like 1 over n plus something. So bigger denominator, smaller number. Oh, bummer. Gosh dang it. Okay, so the comparison test is very, very difficult to use here. Okay, so let's use the limit comparison test and use 1 over n. Because we can, when we do infinite limits, it's okay for us to make this like a 1 over n basically, right? So sometimes when you see these nasty ones like this, you can kind of manipulate that out. What's that equals? Because this is basically like saying n, right? Root of n squared. So, okay, so if L is 1, and the series B sub n diverges, we know that harmonic series diverges, right? Determine that. What does the test say? Okay, we're in the A. Remember that contrapositive I told you about? It works here. So they both have to diverge. Okay. And do note they are both positive. It really should be, yeah. At some point you need to make that statement. You can use this test. And also, positive or 0. Well, we're going to talk about that. Yep.
Do you think it's similar because it's just going up instead of down?
The sequence, you mean? You could make that argument. Okay. We're at 2.3 still. The comparison test, here are the problems. I'm giving you the test to use. Of course, I will remove that scaffold. That's point in the next day or two. A limit comparison test.